All right, so chapter 6 is going to start really the second major part of the class, which is on trigonometry. So, first thing I want to do is just take a look at the word and see if we can break it down and kind of figure out what it means. Does anybody recognize anything within that word? Either a prefix or a suffix or anything? Yes?
Is it metry, the measurement of?
Yeah, metry means measurement. And we see that in different subjects like trigonometry, geometry. I guess that's it. But that's all I can think of. So yes, we do see metry, meaning measurement. What else? Anyone recognize? Yeah?
Is it try, 3?
So try, yeah, part means 3. Anything else? There's something else there that's part of a lot of other words, probably from geometry. Yeah, Caleb?
Gone.
Gone. What does that mean?
I think that's like shape or I think it would be size actually.
Yeah, it means like sides, right? Or sided. So octagon is 8-sided, pentagon 5-sided. Well, trigon is 3-sided. So what we're really looking at is measuring a shape that has 3 sides. So in other words, it's triangle measurement. That's a lot of what trig is. Okay? Creating a triangle and then measuring it to figure out something, maybe an angle or maybe a side. Those are the two big things that we usually figure out. So as an example, let's say, that's kind of a standard example. Let's say you had a house, and you were standing 100 feet away from the house, okay, assuming it was easy to measure the distance between you and the house, just flat ground. And you wanted to figure out the height of, say, the peak of the roof. Well, what you could do is you could measure the angle to the top of the roof, and you can do that with a device called a transit, or you can even make something kind of with a protractor to do it, with like putting a little straw on top of the protractor and using it as like a sight. But the point is, you can get the angle to the top of the roof. And then what you're trying to find is that line in black. Okay, that's the height. And we really just made a triangle. Right? So our triangle would be, let's see if I can, I was going to try to draw it like that. Now, this type of triangle isn't as bad to solve as some of the other ones we work with because it has a right angle in it. Right? And as long as you know a side and you know an angle in a right triangle, you can figure out anything else you want to know. Okay? In this case, the height of the triangle. Yeah, another kind of problem we could have, a little bit more complicated, but let's say that we had a fire somewhere in the distance, and we had 2 towers that could see the fire. So we've got a tower here, and we've got another tower, maybe right here. Those are my towers. And they want to try to figure out where the fire is because they want to give a helicopter or maybe a plane some kind of coordinates to dump water on it or whatever they want to do. So in order to get exactly where the fire is, especially if it is something like if it's maybe foggy conditions and they can't see, the plane can't see the fire until they get close enough to it because maybe there's so much smoke. They have to kind of get, once the plane gets close enough, then they can see it. But maybe the plane's coming from 50 miles away, so they can't see it till they get within maybe 3 or 4 miles. So maybe these towers are within 3 or 4 miles, and they have to figure out where the fire is and give coordinates to the airplane. So the key to something like this is each tower has to be able to see the same object. So as long as the first tower can see the fire, that tower can basically say the the fire is in that direction. And the tower could give a compass heading, right, from where they are to the direction of the fire. If that's the only tower that was there and the only tower that could see it, that doesn't really help a lot because the tower can't say how far away the fire is. They can only say the direction it is. But if you have another tower that can see the same fire, they can also give a direction, okay, where the fire is. And then all we would have to know is how far apart are the two towers. And that would be something that should be pretty easy to look up because it's probably like looking up the distance between two cities on a map. Those two spots are known, and you can just use a map and measure it. So what we have here is a triangle. And we would know the distance between the two towers. And we would have an angle from a compass that gives us the direction to the fire. So this kind of triangle is not a right triangle. Okay, we would have a couple angles here, here, and a side here. Okay, whenever we're solving triangles that are not right triangles, we need three pieces of information. And what you're doing there is called triangulation. Okay, you're triangulating where something is using two different observers. And you can do all kinds of things with triangulation. That's how GPS works. Uses satellites to triangulate where you are. And the more you have, the better. So like if you had a third and a fourth and a fifth tower, or like in GPS, it's more satellites, it can more accurately figure out where you are. Okay? And also GPS is three-dimensional, so then you have to try to figure out how high or low somebody is. Okay? For airplanes, that's obviously more important than when you're driving, but with satellites, you can figure that out as well. So just a couple examples of stuff that we'll do with trig, but a lot of stuff with triangles. Okay, so that's what we'll focus on pretty much in every chapter we do trig. So we're going to start out just by looking at how we measure angles in a triangle, or any shape really, and there's really two main units that we use. Does anybody know one unit that you can use to measure the size of an angle? Yeah.
Degrees?
Yep, you can use degrees. When you get into calculus, you won't. Okay, you'll use another unit. Does anybody know what that unit is? Yep.
Radians?
It's radians. Very good. So it's radians. So we're going to talk a little bit about how we convert between the two. Okay, that's kind of one of the big things for today. So, a little bit of a review about what an angle is. Okay, and this is the definition of an angle that's by itself, a standalone angle, not in a shape. Okay. So an angle is made up of two rays that have a common point where they start from, called the vertex. And it looks something like this. So if you want to draw an angle all by itself, that's generally how you draw it. Right? Two rays coming out from a starting point. Now, when we draw a triangle, the sides of the triangle aren't rays. If we wanted to use kind of a geometric word to describe the sides, what are the sides in a triangle? Yep.
Line segments?
They're line segments. So when we draw a polygon, specifically we're going to focus on triangles, we can say that an angle is made up of two line segments that have a common point. But when you draw an angle all by itself, not in a shape, we usually draw it as two rays. Okay, one ray is called the initial side, and the other ray is called the terminal side. And I'm going to try to explain to you which side is which. So in this angle that I just drew, that would be the initial side. And that would be the terminal side. Okay, so how do you know which side is which? Well, if you have an angle and you go between the rays and you rotate counterclockwise. That's how I would rotate counterclockwise between the rays. wherever you start from, that's the initial. As you rotate between the rays in a counterclockwise direction. Wherever you would end, that's the terminal. So those are the two sides of the angle. Now, there's a standard way we usually draw angles. I think I'm going to mention it in a minute, called standard position. We usually like to always put the initial side being horizontal and pointing to the right. So like if you were asked to sketch, say, a 90-degree angle, the standard way to do it would be just like that. Initial side pointing to the right, and then terminal side pointing wherever you need the terminal side to point to create the angle they want you to create. Now, if I group those together, group them together, I mean, that's still a 90-degree angle, but that's not normally how we would draw it. Okay, we like the initial side usually to be horizontal, and then it makes it even easier to figure out which side the initial side is. Yeah.
I'm assuming that when you find the distance between the two, it's always like the shortest distance, not the longer. Because like, if you went from the long one to the other one, it would still be like, I feel it's pretty obvious with a 90-degree angle, but like if you got something like a 179-degree angle, it seems like it would be easy to mess up, like which side was the terminal side and which side was the other side, because there are similar distances around.
Yeah, so we always want to go with this distance that would be shorter,
Okay.
the shorter rotation. When we're measuring angles, yes, technically there are two angles. There's what we call the interior angle, and then there's this exterior angle on the outside. In general, we're going to be talking about the interior angle.
Okay.
Okay, I think that's actually what I just said to you. So for a positive angle, positive angles rotate in a counterclockwise direction to the terminal side. Okay, let me actually bring something else up I can show you. All right, so let's take a look at this. This is a diagram that basically allows me to draw angles, and I can only move the terminal side. Okay, so the initial side stays right where we generally like to keep it, and I can rotate the terminal side in either direction. So notice as I rotated counterclockwise, it gives me a positive number. It'd be nice to put a little arrow on that red arc so you could see that I rotated that way, but I rotated counterclockwise, and that's how I got a positive angle. Now, what do you think would happen if I rotated clockwise instead? What kind of angle do you think it would give me?
Negative.
Yep, it'll give me a negative angle. All right, so let me bring that back up. So let's go back to 0. And now if I start rotating in a clockwise direction, you can see that the angle comes out negative. Okay, but it's always looking at the shortest distance between the two when we look at what side is initial and what side is terminal. So any question on that? So in this case, initial side would be the horizontal, terminal side would be the one that's going up and to the right. Right? Even if I rotate it like that, again, initial side would still be the horizontal, and the terminal side is the one that goes up and to the left. All right, again, we're going to try to make it clear that the initial side is always going to just be the horizontal. That way, we don't have to look at it like it's been rotated. It makes it easier. All right, so just another way of explaining the same thing, mentioning what John said. We really do have two angles here, but when we're looking at the initial and the terminal side, we want to think of the two rays, rotate counterclockwise between them. Wherever you end up is the terminal side, and wherever you start is the initial. Any questions on that? Okay. Okay, when we want to name an angle, okay, a lot of times we have certain variables that we're used to using. Right? Like when we do graphing in algebra, we use x and y. X is usually the horizontal, y is the vertical. Well, when we have to find angles and we don't know them, we have to give them a name. Most of the names that we're going to use for angles are Greek letters. We are not going to talk about all these Greek letters today, but these are some of the Greek letters that you'll see when we discuss angles. Does anybody know the name of the first one? No, John?
Alpha.
Yeah, that's alpha. So that's a Greek letter that we'll use quite a bit when we do solving right triangles and study law of sines and law of cosines. How about that second Greek letter? Anyone know what that one is, Michael?
Beta.
Yep, that's beta. These are also all lowercase. There is a capital alpha and a capital beta. These are lowercase. How about that other one? Looks kind of like a Y a little bit. I don't know what that one is. Yep. There is an omega up there, but that one is not omega. That one is gamma.
Oh.
So that's gamma. This next Greek letter is theta. And the last one is omega. And if you've done anything with electricity or resistance, like in physics, you might have seen this symbol. Well, that symbol is also omega. That's capital omega. And that's usually used to represent ohms. So when you study electricity and get into resistance, you'll use that symbol to talk about resistance. Not a Greek letter that we normally use. Okay, so those are some Greek letters that you'll see. So I mentioned to you that we try to make it easy to figure out which side is the initial and which side is the terminal. And that's called drawing an angle in standard position. Standard position means that you have the vertex of the angle at the origin, like if you set up a coordinate plane, and the initial side points to the right. Okay? It's on the positive x-axis. So there's an angle that's drawn in standard position. How about if I did that? Is that angle still in standard position? Wait, Mabel, what's wrong with that?
It's not at the origin.
It's not at the origin. The x side, the initial side is on the x-axis, so that's good. But the vertex isn't at the origin, so we would not consider that an angle drawn in standard position. All right, how about if I did something like this? Just like that. Like that. Okay, is that in standard position? What do you think, Madison?
No.
No, what's wrong with it now?
The initial side isn't on the x-axis.
Yeah, the initial side's not on the x-axis. The terminal side looks like it's on the y-axis, but that has nothing to do with standard position at all. So standard position of an angle, we always want to draw it just like that. All right, so let's talk a little bit about how we measure angles. So degrees is one unit that I think someone mentioned right away. And degrees is fine, okay, for measuring angles, but really when you really start to get into calculus and doing a lot more with angles and differentiating and integrating with trig functions, we want to start using radians, right? So the hope is that by the time we're done with trig, you're just as comfortable with radians as you are with degrees. Okay? At first, you might have to change things from degrees to radians to either visualize it or work with it, but the hope is eventually you don't have to do that as much. Okay? So let's talk a little bit about some different measurements that are common. If you had one complete rotation on a circle, how many degrees would that be? John? 360. Now, specifically, if you go in the counterclockwise direction, that would be positive 360. So let's draw a positive 360. Here's 0. And I want you to notice where the initial and the terminal sides are. And here's 360. How do the initial and the terminal sides compare between a 0-degree angle and a 360-degree angle? Yeah,
They're in the same position.
they're exactly the same. And there's a name for that that we'll talk about in a couple minutes. Okay, but when I added 360, I have exactly the same initial and terminal sides as when I had 0. How about if we did a half revolution in the counterclockwise direction? What would that be, Caleb?
180 degrees.
So counterclockwise is the positive direction, and that would be 180. How about a quarter of a revolution in the counterclockwise direction? How much would that be? Mabel?
90.
That would be 90. So again, angles that are measured in the counterclockwise direction are positive. I think we already kind of touched on that. And angles that are measured in the clockwise direction are negative. Now, given the choice of working with positives or negatives, which type of angles do you think we would prefer? Because it's easier. No. We would prefer to work with positives. Okay, that would always be easier than working with negatives. You can also have angles that are more than 360 degrees. Okay? All that means is you've gone around more than one time. Now the application of that to like solving triangles and finding angles in triangles, that doesn't really apply because we have limits on the angles in a triangle. But when we're just talking about rotations, we could rotate around as many times as we want and get an angle. The hard part, though, can be if I said to you, I want you to tell me where the initial and the terminal side would be for an angle that's 1,170 degrees. That can be kind of hard to think about. So we're going to talk about a way that we can take a problem like that and make it a little easier to figure out where the initial and the terminal side would be. Because all we've done is gone around a bunch of extra times. Well, we want to take those extra times we've gone around out of the problem. And just say, okay, where would we be if we didn't go around all those extra times? What would be the simplest angle that you could describe to me that would have this initial side and this terminal side? Okay, so we'll look at how to do that. But does anyone think they could tell me what would be the simplest angle that would have the same initial and terminal side as 1,170? Yeah?
90 degrees.
90. It's exactly the same as a 90-degree angle if all you're considering is the initial and the terminal. And 90 is a lot easier to visualize than 1,170. So 1,170 and 90 degrees, those angles are what we call coterminal. Angles that are coterminal have the same initial and terminal sides. How do you think I could get another angle that's coterminal with 1,170 degrees? I mean, we have 90, that's one. What else? But what could I keep doing here? Yeah?
Add or subtract 360.
Right, that's the whole key. I could add or subtract 360 to keep finding other angles that are coterminal with the one I started with. Okay? All these angles that I keep stopping at are coterminal with 90 degrees. And it's great if you've got a little interactive thing and you can just spin something around to find them, but you don't need that. All you have to do is add or subtract 360 degrees. All right, so let's try a couple problems where we sketch an angle and then find some angles that are coterminal with it. They may ask you to find an angle that's positive and coterminal, or they could ask you for one that's negative. All right, so sketch the angle, find a positive and a negative coterminal angle with what is given. All right, 30 degrees. So I'm not looking for you to really get like a protractor out and make it perfect. I'm looking for you to estimate roughly what 30 degrees would look like. So what you want to do to estimate it is just kind of imagine, all right, 30 degrees. Well, this entire quadrant is how much? It's 90, so that's 1/3. So we're basically going to be drawing an angle that's less than half. It's a little bit less than half. So 30-degree angle would look in standard position. There's your initial. And your terminal side, well, might be something about that. Okay, so let's find coterminal angle. That's positive and negative. Okay. Can someone give me an angle that is coterminal with 30 degrees and positive? There's an infinite amount of them, but just give me the simplest one you can, like the next one after 30. Caleb?
390.
390, yep. And you could add 360 to that again to get another one. How about an angle that's coterminal with 30 degrees and negative? Sophie? Negative 330. So given the choice, if I had to do a trig problem, I would prefer to work with 30 because when we start doing trig, let me show you an example. If I take the sine of 30 degrees, I get that number, 1/2. If I take the sine of 390 degrees, 1/2. If I take the sine of negative 330, 1/2. The point is I'm showing you that angles that are coterminal evaluate the same way when you use them in a trig function. So the easier the angle is, but I think easy means smaller and not negative. So that's generally what we try to shoot for. All right, let's take a look at 145. Okay, so where would that one be? Let's just start by kind of narrowing down the quadrant. 1, 2, 3, or 4. About 2? Yep.
2.
Yep, it's going to be in quadrant 2. So somewhere in here. Now, can anybody be a little bit more specific about where in quadrant 2? And what you could kind of do is say, well, is it kind of in the middle, a little more than the middle, a little less than the middle, closer to being straight up, closer to being horizontal to the left? Yep.
I'm going to be like a little past the middle.
Little past the middle. 135 is exactly in the middle. That's between 90 and 270. So 135 is the average of those two. 145 is a little bit past the middle. So maybe, I don't know, something kind of like that. All right, so there's my angle. And now, let's write down one that is coterminal and positive, and coterminal and negative.
Do you mean, on the curve, do you mean 90 and 180?
Yeah, thank you. Yes, 90 and 180. 270 is at the bottom, and this is 360, which is the same as 0. Okay, what's an angle that would be coterminal with 145 and positive? About Sophie.
Positive.
Positive.
Or 505.
Let's see. So if we add 360 to that, we're going to get 405. 505. Yes, 505. And Annalise, how would I find an angle that's coterminal with 145 and negative?
Would you subtract it?
So subtract how much?
360.
360. So let's do 145 minus 360, and we get negative 215. Okay, any questions on that one? All right, do I have another one? Okay, negative 45, that's fine. So let's put the initial side right there. Where's the terminal side going to be this time? Negative 45. Yeah.
Quadrant 4.
Yeah, that's going to be in quadrant 4, and it's going to be right in the middle. Just like that. You don't have to put that arrow, but that's the direction of rotation that we did. That's negative 45. All right. What would be an angle that is coterminal and positive? John?
Would be 320. We're sorry, no, 315.
315. Yep, so 315. That's the angle that's coterminal and positive. And how about one that is coterminal and negative? Yep, yep.
Negative 410.
Negative
400. That doesn't make sense.
negative 405. 'cause
405. Yeah.
just subtract 360 from that. So it's just like adding 360 and 45, and make it negative. So negative 405.
Oh, wow. Yeah, that makes sense.
Okay, questions on that? All right. So I'm going to give you guys a few different definitions, and I'm going to use a variable in the definition, and that variable I'm going to use is theta, and that represents an angle. What's the definition of an acute angle? Talk about an acute angle, Annalise.
An angle smaller than 90 degrees.
Smaller than 90, and there's one other part to it. Caleb?
Greater than 0.
Greater than 0. Negative 10 is not acute. Okay. So an acute angle is between 0 and 90. How about a right angle? Leanne, what's a right angle?
Like exactly 90.
Exactly 90. So that's an angle that would equal 90 degrees. How about an obtuse angle? John?
It's greater than 90, but less than 180.
Greater than 90, but less than 180. Yep. And all those terms are used to describe a single angle. You could have one angle, they could tell you the measure of it, and then you could classify it as one of these three types. Acute, right, or obtuse. At least if we're dealing with triangles, that's all you'd have to ever think about. Because angles in a triangle cannot be bigger than 180. Now, complementary angles, exactly what it says right there, has an S on it. This is when you have two angles and there's a condition that they meet. What's the condition to have complementary angles? Sophie?
Do they have to 90?
They have to add up to 90. But they have to also be positive. So what you could say is two acute angles that add up to 90. Negative 10 and 100 are not complementary. Yes, they add up to 90, but negative 10 is not a positive angle. What's the other type of angle that we usually, or other pair that we usually study with complementary? Complementary, and then there's Michael? Supplementary. And what is that?
The two angles add up to 180 degrees.
Yep. Again, two positive angles that add up to 180. So negative 10 and 190, no, that's not a positive angle. So negative angles do not have complements or supplements. So if you're asked to find the complement or supplement of a negative angle, it's undefined. There is no answer. All right, so let's find the complement and the supplement of some different angles. Okay, what would the complement be for 48 degrees? Michael?
42 degrees.
42. And how about the supplement?
132.
So yeah, when you find the supplement, they have to add up to 180. So really, you could just take the complement and add 90 to it, and that would give you the supplement. The 132. All right, how about negative 18 degrees? What's the complement? Yep.
Undefined.
Yep, there's none, there is no complement, undefined. Supplement?
Undefined.
Yep. Can't do it.
That was the answer for that.
Now, I'm going to give you one here that's x, and we can assume that x is,
Positive.
yeah, it definitely has to be positive, so we'll assume that it's greater than 0, and that it's less than 90. Because if it was bigger than 90, and I said, what's the complement of, say, 100 degrees? It doesn't have one. So we'll assume that x is between 0 and 90. So, what's the complement? Yep,
Is it x, 90 minus x?
90 minus x. And what about the supplement? Yep. 180 minus x. So that's in general how you go about thinking of the complement and the supplement. You just take your angle and subtract from 90 to get the complement, subtract from 180 to get the supplement. Questions? Okay. So, radians. That is another way to measure an angle. So I know we're covering lots of little things, so there'll be a good amount of questions to do tonight, but they're all going to be quick, like find the complement, find the supplement, is this obtuse, is this acute, draw this angle, draw that angle. They're going to be very, very quick questions. So let's take a look at this diagram. And actually, you know what, before we even look at it, when you look at the word radians, is there any word from geometry that you could kind of make out of some of the letters that are there? I mean, you might need some other letters, but it kind of looks like a word from geometry. Yep.
Radius.
Radius. And a radian has a lot to do with a radius. Okay, the way I'm going to define it and show it to you. So let's start with this picture. This is what we call a central angle. A central angle is just an angle where the vertex is the center of a circle. So I've drawn angle ACB. The rays CA and CB intersect the circumference of the circle at these 2 points, A and B. If you connect points A and B along the circumference or along the perimeter of the circle, you get what's called an arc. And the symbol for that is arc AB. You could also say arc BA because arcs are not directional. Rays are directional. Okay, so we have an arc here that's we're going to call AB. Now, ray CB and ray CA, they are the initial and the terminal sides of an angle, but they're also the what of that circle? Caleb?
Radius.
They're the radius. So the length of CB is R. The length of CA is also R.
It's not unlocked.
It's not unlocked. Okay. All right. So everyone agrees that these two rays are the radius of the circle. All right. Now, you could measure this arc. Like, let's say, just to be simple, you took a piece of string and you put it on that arc, right? Then you cut the piece of string. Then you could take that string, you could straighten it out, put it on a ruler, and you could see how long it is. Now, does the size of this arc change depending on how big I make that angle?
Yes.
Well, yeah, of course. If you make this angle smaller, the sides would come in and the arc would get smaller. If I make the angle bigger, then the arc could get bigger. Well, there's a special situation that could happen. And the special situation would be that the size of this arc is exactly the same as the length of the radius. That could only happen if you made this angle a very specific size. And it would happen if you made that angle exactly 1 radian. So that's kind of a visual way that you can think of a radian. It doesn't help you to convert between degrees and radians, but it kind of gives you something you could visualize. If you made angle ACB 1 radian, so right there, if that was 1 radian from here to here, then the size of that arc would be exactly the same as the size of the radius. If the arc was smaller than the radius, then this angle would be smaller than 1 radian. If that arc was bigger than the radius, then this angle would be bigger than 1 radian. So as far as drawing that to scale, that's probably pretty close to what 1 radian would look like. That's not that bad of a sketch. It's probably pretty close. I don't think my 2 rays are exactly in the center, so that's okay. All right, so any question on that idea? We're gonna come back to that, I think either later this week or on Monday. But if you make an angle exactly 1 radian, then the length of the arc is exactly the same as the length of the radius. Okay, so that's important. All right, so how do we convert between radians and degrees? Well, like converting between anything, you need a starting point. You need to know something. So let's say, just to do something simpler, I wanted you to convert between feet and inches. Can somebody give me a fact that connects feet to inches? It can be any fact you want as long as it's true. Yep. Yeah, Tim?
Well,
Tim, yeah.
12 inches in 1 foot.
Okay, so there are 12 inches in 1 foot. Okay, how do you know that?
Because that's just a known fact. It's a conversion factor.
Yeah, it's something that's known. It's a conversion factor. So when we start to convert between degrees and radians, there has to be something that's just known, like that. Something that you can start with that you don't necessarily prove, but it's more that somebody decided 12 inches is going to be a foot for whatever reason. Okay. Once you know that, you could convert inches to feet or feet to inches. You give me any number you want. Let's say you said, how many inches in 13.5 feet? All I have to do is put that here, put x there, cross multiply, and I can solve. But this was the whole key. Now, because Tim picked a 12 and a 1 for the conversion factor, does that limit the numbers I could use on the other side? Like, could I only do 13.5? Could I do 14.2 feet? How about 18.7? Yeah, just because he picked a 1 and a 12, it doesn't limit the conversion, the numbers I can use on the other side. All right. So we're going to start with some type of conversion, and just because we're starting with that, it's not going to affect what we can convert. Okay? We just have to start with a fact that's true. Okay? Any fact that's true, preferably the simplest fact we can come up with, but any true fact will work. Okay, so to figure out a fact that is true, we're going to start with this diagram. Okay, and this is a particular kind of circle called a unit circle. All that a unit circle is a circle that has a radius of 1. It's the only thing that's special about it. It's a circle with a radius of 1. If you remember the term, I'm not sure what class you would have studied it in, but unit rate. If you tell someone a unit rate, that means you're giving them a rate that has a 1 in it, like 60 miles per hour. That's called a unit rate. 60 miles per 1 hour. If I said to you I was driving 120 miles per 2 hour, that's not a unit rate. You can make it a unit rate, but I didn't give you a unit rate. Okay, so unit circle has a radius of 1. Now, this is going to be the fact that you have to trust me that this is true, just like you have to trust there's 12 inches in a foot. Okay, we can't prove every single thing. We got to start with something, and this is what we're going to start with. In a unit circle, if you measure an angle in radians, and then you measure the length of the arc, they will come out exactly the same. Okay, so an example. Let's say you had a unit circle and your angle was 3 radians. Then your arc will also be 3, whatever, could be inches, feet, but it'll be 3. If your angle was 4.6 radians, the length of your arc will be 4.6. Okay, so what I'm saying here is the measure of the angle in radians is always the same as the length of the arc in a unit circle. That's the important piece. And you might think, well, wait, is that something specific now? Because now you're talking about just a unit circle. Does this idea apply to other circles? Sure. It's just like in the 12 inches, there's 1 foot. Just because I start with that doesn't mean I can't use it to figure out other things. Just because I'm starting with a unit circle doesn't mean I couldn't apply this to other circles. I'm just trying to find something that is true. That's all I need, something that's true. And a unit circle is an easy way to find a connection between degrees and radians. And that's what I'm trying to do, get a connection between the two. Okay, so let's look at the next thing. If we look at this circle, we should know how many degrees it takes to go all the way around it. Okay, how many degrees to go all the way around the circle? It's 360. My goal is to figure out how many radians to go all the way around the circle. And then once I know that, I will have a connection between degrees and radians, just like feet and inches. All right, so let's think about a very special arc. Let's start with this. How much of the circle does that arc take up? Caleb?
Quarter.
That's a quarter of the circle. And what would be the angle that corresponds with that?
90 degrees.
90. Okay, so just make a little chart. Arc, length, and then the angle that goes with it. So if we had an arc length that was a quarter of the circle, that would be a 90. All right? What if I had something like this? What's the length of the arc in that circle? That's half. I mean, we don't know exactly how much half is, but we know it's half the circle. Half the circle. And what would the angle be that corresponds to 1/2? Yeah? 180. All right, well, let's go even more. Let's say here's my initial side, here's my terminal side. What's the arc length there? That's the whole thing. That's the whole circle. And how many degrees is that? Yep. 360. Now, we just said down here that if you measure the angle in radians to go all the way around the circle, it will be the same as the length of the arc. So to figure out this number right here, there's 2 ways you can do it. Either you already know how many radians in 360 degrees, or if you don't, you can find something that it's the same as. Measuring the angle that goes all the way around the circle in radians is exactly the same as the length of the arc. So all we have to do is find the length of this arc, and that's exactly the same as the number of radians to go all the way around the circle. So how would we find the length of this arc? How would we find the length of an arc that's the whole circle? Yep.
Using a piece of string.
Thinking of something more like a formula.
Ah, okay.
Yeah. Thinking of a formula. Yep.
2 times pi.
2 times pi times what?
R squared.
Just r. So we're looking at a very specific arc. We're looking at what's called the circumference. But if we can find the length of the circumference, which the circumference is an arc, the length of the circumference will be equal to the radian measure of the angle that goes all the way around the circle. So let's find the circumference. What's the radius in the circle? 1. So the circumference is 2 pi. And the length of the circumference, which is now 2 pi, is exactly the same as the number of radians to go all the way around the circle. So the arc that goes all the way around the circle is 2 pi. So how many radians would it take to go all the way around the circle? Yep.
6.28-ish.
Yeah, which would be what if you just left it exact?
2 pi.
2 pi. So by using the special fact that on a unit circle, the size of the arc and the size of the angle in radians are the same, and we know how to find the size of the arc, specifically the size of a circumference, the circumference goes all the way around the circle. If you can find the measure of the circumference, it's exactly the same as the number of radians that go all the way around the circle. Okay, so you have 360 degrees equals 2 pi radians. What could we do on both sides of that to simplify it a little bit? Yep.
Divide by 2.
We could divide each side by 2. So we could say that in pi radians, there's 180 degrees. But whenever you tell somebody how to convert between two things, what number do you usually put in the conversion so it's easier for them?
1.
1. Usually you put a 1. If I was going to tell you how to convert between seconds and minutes, I would say there's 60 seconds in a minute. I wouldn't tell you there's 180 seconds in 3 minutes. True, but that's more complicated. So we try to put a 1. Let's get a 1 on one side of this equation. Doesn't matter which side right now. Let's see if we could get a 1 on the left. What would I do on each side to get a 1 on the left? John?
Divide both sides by pi.
Divide both sides by pi. So let's divide by pi, divide by pi. Now we have 1 radian equals 180 over pi degrees. So you could figure out what that is if you wanted. 180 divided by 3.14, that's about what 1 radian is. I don't really care what 1 radian is. That's not why I did that. The reason I did that is because I want to look at a pattern. What if I now wanted to figure out what 2 radians is? What could I do to both sides of that equation that it would give me a formula for 2 radians? Because I have a true fact right here. So as long as I do something that's the same on both sides, I can get another true fact. Yep.
Multiply by 2.
I could multiply each side by 2. And if I did that, I would have a formula that says 2 radians equals, and I have a calculation I could do out. What if I wanted to know a formula for 5 radians? What could I do on both sides to get a formula for that? Yep. Times 5. So what I'm trying to show you is if whenever you want to convert from radians to degrees, all you have to do is take what you're trying to convert and multiply it by 180 and divide it by pi. That's always the conversion from radians to degrees. Multiply it by 180 and divide it by pi. And I think I write that down. Okay, I did that one first. So we'll do this one. Radians to degrees, multiply by 180, divide by pi. Now let's go back and look at it again, but let's get a 1 in a different spot, and hopefully that'll help you to see a pattern to convert the other way. Or you might already have an idea of how to do it. All right, so let's go back to pi radians equals 180 degrees. How could I get a 1 on the right? Yeah.
Divide each side by 180.
Divide each side by 180. So now I have 1 degree equals pi over 180 radians. That's still true. I started with something that was true, divided both sides by 180, and I have something else that's true. What if I wanted a formula to convert 3.5 degrees to radians? How could I take this equation and modify it so it gave me the answer for 3.5 degrees? Yeah.
Multiply each side by.
Multiply each side by 3.5. Again, I don't really care what 3.5 degrees is. The point is, whenever you're trying to convert from a degree to a radian, you take whatever you want to convert, you multiply by pi, and you divide by 180. Multiply by pi, divide by 180, and that will convert you from a degree to a radian. Multiply by pi, divide by 180. Now, these two steps are kind of easy to mix up. One of them is multiply by pi, one of them is divide by pi. I'm going to show you an easy way to remember it. Yeah.
So if we had a different circle, would this be different, or is it still the same?
No, it's just like once you know that there's 12 inches in 1 foot, well, what if you had a different length thing? What if you had 3 feet? Could you still use that there's 1 inch and 12 feet? Yes. Because this is a fact that is universally true about length, and you can use it on any length that you want. This is a fact that is universally true about degrees and radians, and you can use it on any degrees and any radians you want. It's exactly the same idea. All right, so in order to remember which way is which here, all you have to do is think of 2 things. When I say degrees, what I want you to think of in your head is 180. Okay, so when you see degrees, I want you to think 180. When you hear radians, I want you to think pi. So radians, think pi. Degrees, think 180. Just remember those 2 things, and then everything we wrote right here will be automatic. Okay. All right, so let's try to convert that into radians. So you have 2 choices. It's either going to be pi over 180, or it's going to be 180 over pi. If you think of 30 as a fraction, what you want to happen here is you want degrees, which is in the top, to cancel out. Where would degrees have to go in this fraction on the right to cancel out degrees in the top on the left? Yeah.
The bottom.
Would have to go in the bottom. If you want to cancel something out in a fraction, it needs to be in the top in one and in the bottom in the other. If degrees is in the bottom, that means your other unit is in the top. What number did I always say to think of when you think radians? Yep, Mass.
Pi.
Yep, think pi. And what number did I say to think of when you see degrees? Yep, 180. Now, we just reduce what we can. Most of the time, you're not going to round these off to decimals. 30 goes into itself once. 30 goes into 180 how many times?
6.
6. So the final answer here is pi over 6. And that's how you write the final answer. Does it look like I might have left anything off the final answer that you thought should be there? I didn't, but does it look like you think something should be there? Yes.
A unit level curve.
Yeah, the unit label. Okay, we don't put a label on radians. I kind of did the first time here just to get you used to it. But you have to get used to not seeing RAD. So then how do you know if it's RAD? Well, if you're writing a degree, you have to put the little circle. If you're talking about an angle and you don't see the little circle, then you know it's radians. Okay, that's how you know. Yep.
Do you want us to not calculate the pi when we convert?
Most of the time, we are not going to calculate that out. If they want us to, they'll say round to 2 decimal places. Generally, with angles that are multiples of 30 and 45, you don't do them out. And that's why, I don't know if you noticed on this chart, but when I hit certain angles on here, like all of a sudden when I hit 30, it changed to pi over 6. When I hit 45, it changed to pi over 4. So there are special angles, mostly multiples of 30 and 45. Some of the 15s too we could do, but don't do it out unless they say to. All right, let's try this one. Converting 45 degrees. All right, what would go in the top for this one? What unit? Radians or degrees? Yep, Matt.
Radian.
Radians would be in the top. We want degrees in the bottom, so it cancels out. This is the last time I'll write RAD, because I want you to get used to not seeing it. Number with radians is pi. Number with degrees is 180. And what would that reduce to when you do that out? Caleb?
Pi over 4.
Pi over 4.
Just curious, why don't we use the unit rad?
I don't know why they don't put the label on it. Maybe because in calculus you're writing angles so much that just to not have to keep writing these 3 letters over and over. Because there's really only 2 units. If we had like 10 units we could measure angles in that we used all the time, then we'd probably have to write a label. But where we only have 2 that are used common, we can just simplify it and say, well, if you see the one with the little circle, it's degrees. And then if you see the one without the little circle, then it's just a radian, and you don't have to write RAD. So I think if there were more options for angles, we would have a problem. Yeah. All right, and let's do 60. Okay. So how about, Lindsay, what am I going to multiply by this time?
Pi over 180.
Yep. We want pi in the top. We want 180 degrees in the bottom. You do need to put the degree symbol on the 180. Those cancel out. And what do we get when we convert 60 degrees into radians? So, pi over 3. I think I might have one that's a decimal. Yeah, we'll do a decimal when we finish up. Okay. Now, let's try converting the other way. Now, if you want to pretend like RAD is written right there, it's invisible, RAD, but it's right next to the 3 pi. So, I'll put it this time. Where would you want radians to go to cancel out this time? Caleb?
In the denominator.
In the denominator? Which means, what are we going to put in the top?
Degrees.
We're going to put degrees in the top. And the number that we always put with degrees is how much? Yep.
180.
180. And the number we put with radians? Maybe? Pi? Okay, so radians is gone. What else is gone? Not even reducers. What else is gone completely? John?
Pi.
Pi. And now we can do 2 into 180, and then just multiply whatever you have left. 3 times 90, and put a degree symbol. Okay, what's the answer? Mike?
Would you use our calculators for this?
If they're asking you to leave it as an exact answer with pi, like if you needed it to divide 180 by 2, you could. But other than that, you don't want to write a decimal.
Okay.
So what's the answer here? Yep. 270. Okay, so on these last ones, you might see directions that say leave your answer as a multiple of pi. And that's what we did in A, B, and C. Those are multiples of pi. Let's do one more. Do I have a negative? No, it doesn't matter. Negative doesn't change how we do it. Okay, what would I multiply by here to convert from radians to degrees? John?
180 over pi.
180 over pi. Now, when I do this one, pi over 3, pi over 4, pi over 6, those are ones that I have memorized. Those are 30, 45, and 60. Pi over 3 is 60, pi over 6 is 30, pi over 4 is 45. Since I know pi divided by 3 is 60, I know this is just 60 times 2. And that's how I would do it in my head, just because I have some of the basic ones memorized. At first, you might not, so just do it like we just showed. Divide 3 into 180, you get 60, and you get the exact calculation that I said right away, 60 times 2. Now, if you wrote your answer like that, would that be right or wrong? Wrong. That's wrong. It's 120 radians. So if there's a box on the test that's empty and you don't put the degree symbol in the box, then it's wrong. If the degree symbol is already printed outside the box for you, then that means I took care of it and you don't have to worry about it. In that case, I probably wouldn't even make the degree button pop up as a choice to use it. Okay. So just pay attention to your answer and see, okay, did you put the degree symbol or do I need to put it? Okay. All right, so this is one that is not a multiple of 30. It's not a multiple of 45. It would be a pretty common answer that we would round to 2 decimal places. Where would degrees go if I want to change this to radians? Bottom? And radians? Top? So pi over 180. The big thing here is just make sure you use the pi button. Don't use 3.14. Because if I'm asking you for an answer that's accurate to 2 decimal places, and you use 3.14 instead of pi, it's probably going to mess your answer up. So 500 times pi divided by 180, so it would be about 8.73. No label needed because it's radians. Yes, you could reduce by 10. You could make it 50 over 18, but what's the point? You're just going to type it in on the calculator. So I wouldn't even reduce. This is pretty much the same thing, just converting the other way. So I'm not going to go through that one. All right, so those are the problems for tonight, and that's going to cover everything we did, finding a complement, supplement, coterminal angle, converting between degrees and radians as an exact answer and as a decimal, and then converting from radians to degrees as an exact answer as a decimal. So again, I think you'll find most of them pretty quick, and I tried not to give you a ton of the same type. usually just up to 3 questions of the same skill. So we will look at that tomorrow. That's probably the only thing that we'll do tomorrow. It'll be review day. And then Friday, remember, no test. Okay, I will be after school today if anybody needs to see me about anything or review. Probably the last day I'll be after school before your tests next Tuesday. Yes?
Is the test only gonna be on unit 6, or chapter 6?
The test will be on what we did Monday, well, this week and next week.
Okay.
So it will cover the end of chapter 5, which is Monday, Wednesday, Friday, and then next Monday.
Okay.
Yes?
Still come on the 9th period.
Sure, yeah.
Wait,